All right, so I want to come back to SU3, partly because the problem that I gave you is in SU3. So we'll do some discussion of the SU3 case. Now I'll go into a few things in a little more detail than we did for SU2, where we were focusing on more formal things. So SU3 would have Gell-Mann matrices instead of the Pauli matrices. There's two bases that you can use. You can either use this basis, which is like enumerated 1 to 8, or you could use the charge basis. And if you use the charge basis, then often you write it out as a matrix like this. On your problem set, you're free to pick which basis you want to use. It may be that one or the other is easier, but I can't even tell you which one is easier since I don't remember. So sometimes one or the other is easier to use, and you have a freedom of what basis to pick. If you expand, in this case, the trace of sigma mq dagger plus mq sigma dagger, which is that term that had a V0, then that gives you mass to the mesons, as it did for the pions. Because the symmetry group is bigger, you get more predictions. Here you get predictions for the kaon masses, and you get things like the fact that the neutral kaons have masses over md plus ms. And you get things like eta pi 0 mixing, where there's a mixing matrix. So if you look at the masses of eta and pi 0, they're actually non-diagonal. So for the eta in the pi 0 system, you actually get a matrix. So m squared is a matrix. And the terms, so for example, for the pi 0, it was just m up plus md. And but then once you're in SU3, there's actually a mixing term. And there's like an m up minus m down term here that is mixing between, and then same thing over here. So the etas and the pi 0s actually are mixing, and then there's something in this entry. And the mixing is isospin violating in the sense that it's m up minus m down, so it's a small effect. But this is something that you can predict from the Carl-Lagrangian something about, because it describes isospin violating effects from the quark masses. So the reason that I mention that is because often when you do calculations, keeping track of MUs, MDs, and MSs all as separate independent parameters is a little much. And so you want to make an approximation. And so if you make an approximation that ignores isospin violation, so we often ignore isospin violation. Isospin violation is very small. And if you remember, for the SU3 case, you're expanding in ms over lambda QCD, or mk over lambda chi. So it's not a great expansion. You have something like a third. So ignoring isospin is perfectly valid if you're expanding in a third. So basically, because there's a hierarchy between the strange quark mass and the down and the up, you want to focus on places where you get the largest corrections. And one way of making an approximation that allows you to do that is to ignore isospin and take mu equal to md. So if we take mu and md to be some m hat, which you can, if you want an exact definition, you could say it's the average, and you drop the difference. And then you can think of the strange quark mass as being somewhat bigger than m hat. That's an approximation that you can use on your problem set, for example. So let me write out here what all the terms in the Carl-Lagrangian is. And I'll do it for a case where we include in our chiral Lagrangian one other type of coupling, which is this left-handed current that we talked about last time. So we talked about a spurion analysis for the chi term, and I said you could do something similar to couple in a left-handed current. And we had this, where d mu sigma was partial mu sigma times the left-handed current sigma. So we thought of it, putting it together into a covariant derivative. And if I do that, it modifies the leading order Lagrangian and just makes these partials into covariant derivatives. Power counting. For power counting purposes, you count sigmas as order 1. You count d mu sigma as order p, which means you count L mu, the source, as order p. This is a left-handed source. And you count chi's and mq's as order p squared. That's just repeating what we've already said. And these higher order terms, which were L's, we can then enumerate. And I now just use D's, covariant D's, when I write them down. I'm now in SU3, and it turns out that one of the relations that we used in SU2 doesn't carry over to SU3. So if I just think of guys with 4 covariant derivatives, it turns out that there's one more operator there. So there's those two, which we talked about, L1 and L2, and then there's also an L3. So we can't get rid of this guy. I'm always writing sigmas next to sigma daggers because of the chiral transformation. I'm also imposing parity, though I'm not going to spend much time talking about that. And really, I want to enumerate also for you some of the terms that involve the quark mass chi guy. So you could have a guy that's a cross term. This would take care of the renormalization of things like p squared and pi squared times 1 over epsilon. That's L4, L5. We could also have the quark mass type term just squared. So take the trace and square it. That's L6. It turns out that we could also build something with the right parity by just having the difference instead of the sum, and that's a different operator. So that's L7. We're going to go up to 9. Don't be afraid. You could have something with 2 sigma daggers and 2 chi's, which is another way of building a chiral invariant. And then for parity, you need the other way. And then finally, something called L9, which involves a trace that involves L mu nu, where L mu nu is built out of this external current. So we can take 2 of our covariant derivatives and take a commutator. And that's giving the final operator. So there's a complete basis for SU3 for a left-handed current and a chi. Yeah, I'll write it down. Yeah. So if L mu is something that has SU3 indices, has an SU3 matrix hiding inside it, then there's a commutator term as well. And then it's just this combination. I also used the equation of motion. And I didn't talk about it, but I used the equation of motion, and I used SU3 relations. Much as I talked about for SU2, there's some SU3 relations that survive, and I got rid of some operators doing that. Now, you could say, well, I have this SU3 and SU2, so why don't I try to relate them? One of them has a kaon, the other one doesn't. The one without the kaon thinks about the kaon as a heavy particle. The one with the kaon thinks about the kaon as a light particle. Those are two theories. I could try to make them match up with each other. And that's something that you can do, actually. So there's a little bit of a lesson there, so that's why I want to mention it. So SU2 and SU3 seem like they're describing similar physics. They both could describe pions. They both have pions in them. But the SU3 has more. It's got the kaon. That means that in the SU2 theory, the kaon is in the coefficients. OK? So if you do a correspondence, you get relations that are like this. So the 2 here means SU2. And where I don't put any subscript, it's SU3. And something that, this is a 96. And if you really do that, what I said, compare observables, you get relations like this one, where you actually see the kaon is showing up from on this side and is being encoded in coefficients in the SU2 theory. So what you think of as the coefficients in your chiral theory depends on the matter that you've put in, including things like what particles like the kaon, what group you're talking about. This is an explicit example of the kaon being in the coefficients if we use SU2. OK, so just like in SU2, we have to go through a normalization of the LIs. And you can think of that by writing a formula like this one. Bare Li is equal to some renormalized one, which I put a bar on top of, and then a counter term. And the counter term will be some coefficient, some number of 4 pi's, and then some epsilons. And just like in gauge theory, we get rid of the Euler gamma and the log 4 pi. We have an MS bar type definition. And in chiral perturbation theory, people often take an extra 1 along with the ride just because they're allowed to. Because it tends to show up in the kind of loops that you encounter. So sometimes that's included, sometimes it's not. So for example, as an example of a diagram, you could think about this one. And that does cause mass renormalization for the physical boson. So if you think about our lowest order relation as where we started, let me write that as m0 squared is 4v 0 over f squared, mu plus md. Sometimes people call this, well, making up more notation. Yeah, which I'll use in a minute. And so if you actually calculate this loop, then you get a correction to that formula. This would be m pi squared, but you would get a correction. If you did it in SU2, just to keep the formula a little simpler, then it would look like this. So M0 is like the pion mass, but the pion mass at lowest order in the chiral expansion. So it's not the physical pion mass. So 2 L4 bar, in theory 2, with 2 flavors, 2 SU2, plus an L5 bar, minus 4 an L6 bar. So these various coefficients are coming in with some numbers in front, some combination of them. And then there's some contribution from a chiral loop. And if I take away that 1, it's just a chiral logarithm. So this is 4 pi f squared log m0 squared over mu squared. There would be an extra term with just plus 1 times this if I hadn't gotten rid of that, or minus 1 times that. OK, so this is from the loop. This is from the explicit 4-dimension operators that were of the higher dimension, some combination of them. The divergence, the UV divergence, is absorbed in some combination of them. And if you want to figure out exactly how the UV divergences go in between this, then you've got to think of renormalizing more than just this diagram. And you can generically think of observables as having this kind of expansion in MU and MD. So if you like, you should think of M0 here as really just M up and plus M down. This is saying at lowest order in chiral perturbation theory, there's a linear term. But then here, there's an M0 to the 4th term, which is quadratic in the quark masses. And there's also a quadratic term from the loops. So you have an expansion in the quark masses. Think of M0 as the quark masses, and M pi as the meson mass. OK, and this is, I just gave you the example of the pion mass, but this is generically true for observables that you might calculate that they have this type of result where you have an expansion.
Is there any physical reason for why the mass square of the meson scales linearly with the mass of the quarks and not like?
So one way of saying it is, yeah, so you might think, well, why is it not M pi equals MU and MD? And the glib way of saying it is, well, if you think about M pi squared and you think about it having an expansion, then it could have a constant plus linear term plus quadratic term. You don't have the constant because of the chiral symmetry, so the linear term is the first thing that's allowed. That's one way of saying it. I mean, if you think about it, in the bosonic theory, we have the Lagrangians quadratic in masses, right? Whereas in the fermionic theory, you have linear in masses, and that's also part of what it had to do with. But it's really a combination of symmetry breaking and that. It's allowed, so it happens, is kind of the bottom line. But it's allowed by the symmetries. OK, and so finally, this is the example I'm actually going to get you to do. So I'll have you look on the problem set at decay constants, and they have an analogous result to that one. You'll do the calculation in SU3, and the kind of result that you should expect to get is something that looks like this. So I'm using this B0 notation that I introduced over there, just so I could write it all in one line. And these mu's with the subscript I are just some shorthand for some contributions coming from loops. And F is the result in L0. Well, so F is the parameter in L0, whereas F pi is the physical decay constant of the pion. So one result which is encoded in this formula is that the Lagrangian parameter is actually equal to the decay constant at lowest order in chiral perturbation theory. That's something I didn't cover. I cover it when I teach quantum field theory 3. You can look at my notes to see that derivation. Those of you that have taken QFT3 from me, you've already seen that. And basically what I'm asking for on the problem set is I guide you with several parts, but and how to think about these higher order terms. What are the loop graph contributions? How do you get these terms from the higher order Lagrangians? How do you put it all together? It's a nice example of this use of chiral perturbation theory. And again, we see that a physical observable, which is this decay constant, has a chiral expansion. And the thing that chiral perturbation theory is actually doing is allowing you to predict both the form of that expansion as well as these things here, which are called chiral logarithms. So if you ask about predictive power, the polynomial terms of higher order in the quark masses that are polynomial, you end up having unknown coefficients. But the terms with logarithms have coefficients which are fixed by your lower order Lagrangian. So those are things that you predict with the chiral perturbation theory. When people do lattice calculations, they need to do chiral extrapolations, and then they're using formulas like this one. OK, so any questions about that?
So that m pi there is what's the physical mass?
Yeah, physical mass. This is the physical mass. This is the quark masses. M0 is just this combination with m up and m down.
Okay, so the mu dependence cancel between.
And the mu dependence cancels because these guys all depend on mu. Yeah. And same thing here. These guys depend on mu. Here I have just enough room to make that explicit. OK, so that actually covers all the goals that we had for chiral perturbation theory, though it's a fun topic, and there's many more things we could discuss. But that's what we needed to discuss. And so we're going to move on.